will be something like this. Then whether you will prefer mesh analysis or node analysis, that actually depends on your experience. You have to practice questions to gather that, to gain that experience. What I can tell you, this you won't find this thing in any book. This is basically all these things. What I'm saying is basically out of my experience. That if you find the number of series paths and number of voltage sources are more than number of parallel paths and current sources, then mesh analysis is a preferable way. Or if you find that number of parallel branches and current sources are greater than number of series branches and voltage sources in a circuit configuration, then node analysis is a preferable method. So whenever you find a circuit, you just observe the circuit, that whether it is better to use node analysis or mesh analysis. Anyway, going to this point, going to this node analysis, first you identify the node. Then what you need to do, first you have to identify the node. So why node analysis is used? As we have seen in mesh analysis, that using mesh analysis we identify the meshes, then we denote the currents, and using mesh analysis we find those unknown currents. Similarly, in node analysis, we are interested in the unknown node voltages. So as I am saying unknown node voltages, so there must be something like reference node or known voltage. So what is the reference node? Reference node is basically the ground node. In every circuit, you will find two types of nodes. Normally, the bottom node or the lowermost node which is present in a circuit is considered as a datum level or reference node or ground. So for which you can readily assume the voltage as 0. For example, if there are three other nodes, then corresponding voltages can be written as V1, V2, V3, etc. So this is what I am saying, that if there are say n number of nodes, then there will be n number of voltages. But out of these, I mean, among all these nodes, there will be a certain node whose voltage is already known. That means the ground. The ground node is for which voltage is 0. So all other nodes whose voltages are yet to be defined or yet to be calculated, they are called non-reference nodes. Non-reference nodes. If you find in a circuit that there are n number of nodes, then among these n number of nodes, you have to assume at least one reference node, which is a ground node. With respect to this, all other voltages are specified. I shall show you the circuits, then you will get a clear indication of this. So there are n minus 1 number of nodes left whose voltages are not yet specified. So these are non-reference nodes. So what is the procedure? Suppose this is an example. So can you tell me how many nodes are there? Someone tell me how many nodes are there?
4.
Yes, effectively there are 4 nodes. This one, the third node, and as you can see, all these points are basically connected to the same point here, right? So that means all of them are basically grounded. So you can say all of them have the voltage V equals to 0. So effectively there are 4 nodes. If you name them as 1, 2, 3, then corresponding voltages can be written as V1, V2, V3. Okay. Then what you will do, you will see that which currents are entering and which currents are leaving. If nothing is specified, for example, this 2 ampere current, it is specified, it is shown to be leaving the node 1. If nothing is specified, then we assume that the current is leaving in this way. So you can say that the current which is leaving through R1, that should be V1 minus 0 by R1 or V1 by R1 simply. the current which is leaving from node 1 in this direction from 1 to 2, that is V1 minus V2 by R2. As we have chosen the direction of current from left to right, so naturally V1 must be greater than V2, so V1 minus V2 by R2, that should be the current. In this way, either you can do it or you can simply name these currents as I1, I2, and then you can write the KCL equation here at this point. Say I1 and I2 they are leaving, I1, I2 they are leaving, 2 ampere is also. So this must be equal to 0. That should be the KCL. So that is the straightforward way that you have learned already in basic electrical. So I am showing you this. See, I have chosen the names. I have denoted the currents as I1, I2, I3, I4, I5, etc. Now, if you see that in node 1, I1, I2, I2 ampere, all of them are leaving. So that should be the node equation, 2 plus I1 plus I2 equals to 0. If you see the same, if you apply KCL at node 2, so as you can see, applying KCL to each of these 3 non-reference nodes. Which nodes are non-reference nodes then? 1, 2, and 3. Whereas the reference node is this one. This is the reference node for which voltage is specified, I mean 0, and with respect to which all other voltages are measured. How do we measure voltage? If you connect a voltmeter across here, across these two, then you get the voltage here, voltmeter, right? So that means you have to connect the positive part of voltmeter to this point and negative part to this point. So that is why we are saying that node voltages are specified with respect to the ground. Let me erase this part, otherwise this will create confusion. Anyway, so now we have this case for node 1, this is the KCL. For node 2, you can see I3, I4 they are leaving, but I2 is entering. Accordingly, we have chosen sign. Similarly, for node 3, you see that I5 is leaving only. Otherwise, I4 and IS, all of them are entering. Accordingly, we have chosen signs. So these are the node equations. Next, what we do, we convert the currents in terms of voltage by impedance. We convert all these currents in terms of voltage by impedance. As for example, I1 is V1 by R1, I2 is V1 minus V2 by R2, I3 is V2 by R4, I4 is V2 minus V3 by R3, I5 is V3 by R5. Very well known things. So then what we do, we write the node equations, then we convert this into voltage by resistance form in this way. As you can see here, I just replaced those values I1, I2 here, and then we got this equation. For node 2 also, this kind of equation can be obtained. For node 3 also, this kind of equation can be obtained. What next? This thing is you have to rearrange the terms so that you can get this equation in terms of V1, V2, V3 like this. You are rearranging the terms like this. What is G1 by the way? What is G? G is called conductance, 1 by R. Sometimes in a circuit, only resistance will appear. Then corresponding reciprocal can be said as conductance. Sometimes you will find Z in a circuit. So corresponding reciprocal is 1 by Z, that is I. This is called admittance. Admittance is a more general term because resistance is a specific circuit element for which the reciprocal of resistance is conductance, whereas impedance means there could be anything. Along with resistance, there can be inductors or capacitors or maybe some combinations of that. So that reciprocal of impedance is admittance. Anyway, so if you rearrange the terms, then you will get an equation like this for the first node. If you rearrange the terms of the second equation, then you will get an equation like this. So all these equations are actually indicating to a fact. See, these equations have been rearranged. You get the equation like some constant multiplied by V1, then some constant multiplied by V2. If you remember, if you compare all these, with the inspection method that you learned in mesh analysis, then you can see here, actually in this case, in node analysis, inspection method is equally applicable. How? Remember what we did in case of mesh analysis? There we found self-impedance. What is self-impedance? The sum of impedances obtained.
Summation, yes, sir.
Yes, sum of the impedances obtained from a complete round, right? Similarly here, sum of the admittances which are connected to a particular node, that is the self-admittance term. Self-admittance. So for a particular node, say A, we can write this as YKK. General notation. Similarly, there will be mutual admittance terms also. What is mutual admittance? If you compare this with the inspection method of mesh analysis, then here you have found that mutual impedances where the impedance shared by two adjacent meshes. Similarly here, mutual admittance is the admittance shared by two adjacent nodes. So you can call it YKJ. Okay, in between node K and node J, the admittance that lies. So see this equation. The node for which you are writing the equation, first term will be self-admittance multiplied by that node voltage V1. If you go to that circuit, you can see it here. R1 corresponding admittance will be this 1 by R1 or simply G1 you can write. See, all these are connected to what? Node 1. So accordingly, you can get G1 plus G2 multiplied by V1. Similarly, mutual admittance terms like R2. If you take the admittance, that becomes G2. So that G2, that will be multiplied with V2 and so on. However, in this case, we have a difference. Last day I stated that in case of mesh analysis, depending on how you are choosing the direction. If you remember, in case of mesh analysis, if you find say two meshes like this, and if the current directions are like this, then through an impedance, both the directions, I mean the directions of the currents are different. The mutual impedance terms were negative. If you choose the direction in this way, suppose this is flowing, all these currents are flowing in same direction, then the mutual impedance terms will be positive. But in case of node analysis, you need to remember this. You compare the node analysis inspection with inspection method of mesh analysis. Here, mutual admittance terms are always positive. I mean, always negative. The mutual admittance terms, these are always negative. That's the difference. Otherwise, you can see all of them are same. See, G1 plus G, that's the self impedance multiplied by V1 minus G2 into V2. Because remember, R2 was the resistance between node 1 and node 2, 0 multiplied by V3. And here, how do we choose the right hand side? If you remember, in case of mesh analysis, if we find the current is coming from plus sign, then we take positive. If we see that the current is coming from a minus sign, then we take the right hand side as negative. Here, if the current is entering a node, I mean leaving a node here, when you are writing the right hand side of node equations, remember this, that when the current is leaving a node, then that will be negative. If the current is entering a node, IS, that is corresponding term will be positive. So like this. Here, this is -2, whereas IS is positive. So just then rearrange the terms. These are the equation format. You can convert this into matrix format. You get this equation, you can solve it using either matrix solution or whatever way you prefer. Okay, so this is another, not another, rather the same thing where the equations has been written by inspection. So let me show you a document here. Here I have written everything. Hopefully you can observe this document here. The voltages, I mean, there is a reference node you can see in this network whose voltage is V equals to 0. That reference node is D. Other nodes are marked as A, B, and C. So corresponding values, voltages VA, VB, and VC, they are marked. So if you observe for node A, what is the self admittance term? Self admittance. It is the sum of admittances meeting at a node. Of course, in a real problem, I mean, when you will be facing problem in question paper, there you won't find anything in admittance pattern. Rather, you will get the expression in terms of impedance. Okay, so you just need to take the reciprocal. Here, I have chosen a simplified version where already admittances are given, but so that I can show you what self-admittance is. But in the real problem, you will find impedances. You need to take the reciprocals. What is the self-admittance for node A? Y1 plus Y2 plus Y3. So this Y1 plus Y2 plus Y3, that means sum of the admittances meeting at this node, that multiplied by voltage VA. You can see this. That is the first term, and this is always positive, just like self-impedance term we saw in mesh analysis. Okay, then mutual admittance. What is mutual admittance? The admittance shared by two non-reference nodes. Right. Non-reference nodes are which one? This is a non-reference node A. This is a non-reference node B. This is non-reference node C. Remember again, reference node means whose voltage is already known. So actually we are trying to find node equations using which we need to solve, or we will be solving VA, VB, VC. These three node voltages are not specified. So these are the non-reference nodes. Corresponding mutual admittance term is Y2. You can see here Y2. This is the mutual admittance between A and B. Between A and C, the mutual admittance term is Y3. Like this. Y5 is a mutual admittance between node B and node C, and so on. So anyway, what will be the terms? As I said, mutual admittance term is always negative. Y2 multiplied by the adjacent node voltage VB. Y3 multiplied by VC with a negative sign. Here current I1 is entering, so positive. For node B, see at node B, Y2 plus Y5 plus Y4. Y2 plus Y4 plus Y5. Self admittance multiplied by that node voltage VB. Y2 is a mutual admittance between B and A, so negative Y2 multiplied by VA. Similarly, the third term will be, you know, that minus Y5 into VC. No current, I mean, there is a current which is entering I2, so it is plus I2. Similarly, you can write the equation for node C, I believe, node C actually. So that's how the inspection method looks like. So it is very clear from this analysis that inspection method actually saves some time. During exam, you don't need to write separately KVL or Ohm's law for different circuit elements. Then you don't need to do all other things, rearranging terms. So in just like mesh analysis, in case of node analysis also, inspection method is applicable. Okay, I'm going to the.
Sir, repeat the mutual admittance part. The terms, how are you writing?
Yes, mutual admittance is the admittance shared by two non-reference nodes. Okay, suppose if I have a circuit like this, suppose in this way, suppose these two are non-reference nodes and you have an inductor whose impedance is given as J3. Suppose this is node 1 and node 2. So what will the self-admittance term, can you tell me? 1 by J3. Okay.
Yes.
Admittance, remember, it is the admittance shared by two non-reference nodes. So admittance, if this is given in impedance form, then you have to take the reciprocal. Don't forget to do that. Anyway, so let's go to that PPT presentation again. Where is that? This is where we left, I think. Okay, so those points are summarized here. Actually, how to use inspection method for nodal analysis. These points are written. Okay, now see. For your convenience, the corresponding values, I mean corresponding admittance, or you can say in this case the conductance, because this circuit is a purely resistive circuit. So for your convenience, the conductance value is given. I hope you know the unit. This is Siemens S 2 ohm, that is resistance half Siemens. Similarly, for 3 ohm it is 1/3, for 4 ohm it is 1/4, for 2 ohm it is half. So how do we write the node equation then? Tell me, what will be the first node equation?
V1 into 1 plus 1 by 2 for self-impedance.
V1 into 1 plus 1 by 2, yes, then
minus V2 into 1.
Yes.
And plus is equal to, no, plus 2 is equal to 0.
This half plus 1 into V1 minus V2, and 2 ampere is leaving, so it is minus 2. As you said, plus 2 equals to 0. So if
Yes,
you
sir.
take plus 2 at the right hand side, then it becomes minus 2. You see?
Yes, sir.
1 plus half minus 1, 0. Multiplied with V1, V2, V3. That is equal to minus 2. No problem. Write the same for node 2. 1 plus 1 by 3 plus 1 by 4 multiplied by V2. This. Then minus 1 multiplied with V1. Then 1/3 multiplied with V3 with a negative sign, of course. No current is entering or leaving shown here for node 2, so 0. For node 3, 1/3 plus half, that will be 1/3 plus half, that will be multiplied with V2, V3. This 1/3 multiplied by V2 with a negative sign, and node 1 is not connected here, so 0. Here 1 ampere current is entering, plus. I hope there should not be any problem regarding this. That's a very cool method, you can say, using which you can readily obtain mesh equations and node equations for any type of circuits. That's the solution. If you further analyze this, then you may get a solution like this. You can verify that I found those solutions. It is not that it will be correct all the time. You can verify this at home, that whether they are correct. You can choose different circuits also. Let me tell you that though we have actually we need to cover the entire syllabus, so it is actually not possible for me to solve all the problems in a book, right? So it is better that you should start this on your own. You just go through this theory part, you see the example that I am doing, then find some problem from some circuit theory book and try to do this on your own. Okay, fine. So let's go to this. What happens if we have dependent current sources in the circuit? Not a big issue actually. You can see this current source, this current source, all of them are independent current sources. They have their own current. But what is dependent current? Dependent current means it is basically a model using which a certain part of the circuit is remodeled or represented as some dependent voltage source or current source. So that dependent source doesn't have its own voltage or current, rather it is governed by, or its value is dependent on some other voltage and current which are occurring somewhere else. So how to deal with those problems? Wait a minute. Yes. How to deal with those problems where we have dependent current sources? So basically, we need to consider those dependent sources as just like independent sources. And then we express the currents of each dependent source in terms of node voltages. And then we rewrite the equation. So instead of going through these points, rather we can consider a circuit. Then the illustration will be easier. So what we have here, it has a shape which exactly looks like the previous one. The circuit configuration is almost the same. However, here the independent current source is changed to a dependent current source, which is having a value 2i3. Right? If it is 2i3, then how to do this? See, other things are same. G1 plus G2 that multiplied by V1 minus G2 multiplied by V2. Everything is all right. But here, remember, in this right hand side, you wrote IS, simply IS. Here, IS is actually dependent on some other, which current? This current. You can recognize this current I3 is nothing but V2 divided by R4, isn't it? If you can see it here. I3, this is what? V2 multiplied by G4, right? G4 is the conductance. So corresponding resistance will be R4. So V2 by R4, that is I3. Or you can write this as V2 into G4. Once you recognize that I3 equals to G4 into V2, then you can simply use it here. Just substitute that value in this equation and then do the calculation like this. If the values of G1, I mean these values are specified, then you can definitely obtain the values of V1, V2, V3 by solving this matrix equation. Next thing is another problem. A problem with it is an example. Example is dependent source. So would you like to try this? See, the question is to solve the node voltages V1 and V2. Would you like to solve this or shall I show you how to solve?
So you can try.
You can try. You see, in these cases where the branch contains a voltage source, in this case, it is better to use the straightforward way. I mean, if I ask you what is the current through this branch, can you tell me that? What is the current through this branch?
So V1
node
minus
voltage-
10 divided by 10.
Yes, V1 minus 10 divided by 10. Fine. Similarly, what is the current through this branch?
V2 minus 5Vx divided by 4.
Exactly. We would V2 minus 5px divided by 4. In this case, use of straightforward method is more suitable. I mean, it's better to avoid the confusion. So it's now it's obvious, you see that V1 divided by 5, V1 minus 10 divided by 10, V1 minus V2 divided by 2. These are the currents leaving, say, and the 2 ampere current is entering. So accordingly, you can write the equation. So try this. V1 by 5, V1 minus 10 by 10 plus V1 minus V2 by 2. This is equal to 2 ampere. This is the first equation. The second equation will be V2 minus 5px by 4 plus V2 minus V1 by 2. These are the currents leaving. Also 2 ampere is leaving. So plus 2 equal to 0. That's the second one. Now the question is, you have two equations, but there are three unknown variables. One is V1, another is V2, another is Vx. So you have to find this Vx, that means this dependent voltage source value, with respect to some other known voltage or current.
Sir,
So,
V1 plus Vx equal to V2. This is another equation.
yes, exactly. Or you can say that this side is positive, this side is negative. So obviously
Yes.
V2 is greater than V1. You can write this, that V2 minus V1, that is equal to Vx.
Yes, sir. Yes.
The same thing which is written here. V2 minus Vx minus V1, that is equal to 0. Same thing.
So I use KVL there. V1 is equal plus Vx equal to.
Certainly. You see, whenever I mark V1, that means it is the voltage measured with respect to ground.
Yes, sir.
Similarly, V2, that is measured the voltage of this node with respect to ground. So basically, if you consider this entire loop, then you can solve it. Voltage V1 across this, then Vx, so plus minus, that means Vx plus V1, that is equal to V2. You can also go through that way.
Yes, sir.
Okay, then solve it. All those required equations are written. Solve. I wrote those equations in this previous slide. So these are the equations, you just need to solve it.
Sir, one question.
Yes.
Sir, if suppose there is a voltage source between two non-reference nodes, then how to calculate the current through that?
Yes, possible. That is actually a part that you will learn in supernode. Possible.
Oh.
It may happen that in between two non-reference nodes there is a voltage source. That's what you are saying, right?
Yes, sir. Yes, yes.
So that's basically leads to a constraint. just like the super mesh, if you have a current source between two meshes, then how do we represent this? Suppose this is a 3 ampere source in between two meshes, like this. If you choose the currents as I1 and I2, then how do you write this? This is a constant equation, I1 minus I2, that is 3 ampere. Similarly, if you have two non-reference nodes and the voltages are like this, suppose say voltage here VA, voltage here as VB, and this is suppose 5 volt, then you have to find the constant equation, which is VB minus VA, this is 5 volt. And there is another thing, you have to write node equation for this node, you have to write node equation for this node, and then you need to add them to find the super node. I shall tell you this during super node analysis. Okay, so try to solve this. The equations are written. You can multiply this equation by 10, the first equation, to get rid of the denominators. You can multiply this by 4. So what do we have? V1 minus 10 plus 2 into V1 plus 5V1 minus 5V2 is equal to 20, or 3V1, not 3, 3 plus 5, 8, 8V1 minus 5V2, that is equal to 30. That's the first. For this, 2V2 minus 2V1 plus V2 minus 5VX equals to minus 8, or minus 2V1 plus 3V2 and minus 5Vx. Vx equals to this. So minus 5V2 plus 5V1, that is minus 8. What do we have? 3V1 minus 2V2 equals to minus 8. These are the equations you need to solve. Solve them and find the answer. Have you found the answer?
Sir, yes,
So
sir.
V1 coming 20.
V. V1. Take again. V1, I think V1 is 100.
Yes, sir. V 100 और V2 100.
This. V1 is 100, V2 is 154.
Sorry,
Hopefully,
sir. 100.
yes, hopefully these are the answers. Check whether I did this correctly or not. 8v1 minus 5v2 equals to 30. 3v1 minus 2v2 equals to minus 8. Right. So solving this, we can get this. Okay, then concept of supernode, but I don't think I have time to do. So just tell me if you have any question regarding this, then
No, sir. Okay.
here we have difficult problem. Difficult in the sense here the complex values are involved. So here the method has been shown. I shall share this document in Google Classroom. You can find it. Anyway, I am just saying what has happened here. The question is find Ix. This is the current Ix that has been shown in this circuit. Now, whenever this type of values are given, 20 cos 4t, that actually means 20 angle 0. What I said here is a cos 4t plus 30 degree. Then an additional 30 degree is there. So a is the modulus, angle is 30 degree. Suppose this 5 cos 40 minus 36 degree. This means modulus is 5, angle is minus 36. So 20 cos 40, this means 20 is the modulus, 0 degree is the angle. Also you see 20 cos 4t, that means angular frequency omega is 4. If you remember, yeah, angular frequency omega is 4. If you remember, for inductance, impedance is j omega. There are two inductances, L1 and L2. Corresponding impedances are j omega L1, j omega L2. So omega is 4. Use their values. One is 1 Henry, another is 0.5 Henry. Accordingly, we got the impedances. There is also a capacitor. This one, 20 angle 0. That's why the equivalent circuit has been shown in 20 cos 4t. That means modulus is 20, angle is 0. But sometimes you may have a situation like this. Some value constant multiplied by cos 4t plus 30 degree. Then remember it is that value, then angle 30 degree. Or in this case, negative value. So accordingly, everything will change.
Okay, sir.
Okay, I shall share this document in Google Classroom. As I mentioned, install this.
कुछ गुस्सा हो रहा है मम्मी का
Microsoft Windows Journal. Okay. Just install it, you can access all those .gnt files.
Okay, sir.
Okay, so please respond. এটা কি একটু উদয় তো তোমাদের 62 62
Yes, sir.
63
Present, sir.